Thanks everybody for joining. This is a session today about what vast data can do to simplify, to accelerate the Splunk experience. Sitting next to a colleague who didn't have a complete understanding of the title slide, so this is a little girl that's searching, which people do with Splunk all day long. Anyway, so as a way of introduction, I'm Jeff Denworth, VP of Products for Vast Data, and appreciate all of you taking the time to understand our story. So with that, we will get into it. As is always, at least in our second year, we'll continue to kind of just recap what Vast is all about for those of you that are new to our story. We're pretty simple in our mission, and it's a clear one. We're out to kill the hard drive, and the way that we're intending to do this is by delivering a system that combines a new set of capabilities that all come together to basically render the economic arguments for mechanical media as dead. And then our realization is that once you can get to a point where you can afford flash for all of your data, then you don't have the same motivations around storage tiering as you did in the past. So what we've built is a radically affordable flash platform that exposes file and object storage protocols, can be scaled to exabyte proportions, and gives direct attached storage levels of performance to applications. So we've broken a fundamental trade-off that exists between performance and capacity that customers have been wrestling with for the past 20 to 30 years. And on top of that, we've also broken a series of trade-offs around protocols where you don't need to make the same decisions about how to provision infrastructure for your applications based upon either protocol or system boundaries as you have in the past. The architecture is what we call a disaggregated and shared everything architecture. It combines a bunch of new technologies that really weren't available to storage architects before 2018. We made some forward bets on these when we started the company in 2016, and these include a new storage fabric called NVMe over Fabrics. This is a commodity storage protocol that can be layered on top of either Ethernet or InfiniBand networks that allows us to disaggregate storage from compute. You can have essentially an infinite number of containers that we use to basically drive our system, as well as provide access via the different protocols we support. That connect up to an infinite number of SSDs and crosspoint devices, all where the state of the system is stored. So NVMe over Fabrics becomes this transport layer that basically gives us direct attached performance, even though we've completely decoupled CPUs from the underlying media, and every CPU can see all of the data in a cluster. The second bet that we made is for a new type of very low cost, low endurance flash called QLC. QLC flash is the most affordable flash that you can purchase today. As best as we can tell, we're the only commercial enterprise system vendor shipping this in quantity. And the reason that we can do that where nobody else is that we've built a whole new series of flash translation algorithms that allow us to get around 20 times more endurance from these drives than what other architectures can get, making it possible to field them for over 10 years in large environments where we start to blend both transactional I/O and archive data into one global system. The way that we can do that is with the third technology that we bet on, which is 3D Crosspoint. Crosspoint is a new type of persistent memory that's used in environments to kind of blur the lines between memory and flash. It sits between the two in the storage hierarchy. It has the persistence of flash. It has the cost points that are very close to flash, but it has performance that looks more along the lines of what people would expect to see from memory. And so with this, we essentially build the big distributed layer of 3D Crosspoint memory on top of these QLC flash drives to essentially make it possible for the system to order data and migrate it down into flash in a way that the flash wants to be written to, which is very different than how previous systems and previous media sought to be written to. And so 3D Crosspoint is the enabler that allows us to essentially build a platform from the lowest endurance, lowest cost flash in the marketplace. And these two can scale independently. You can build the containers to meet whatever performance that you want. You can build enclosures out in the cluster to get to whatever capacity point that you need. Now, all of the containers expose all of the protocols. Today, we have support for NFS over RDMA. SMB comes in April, S3, as well as we have integrations with various container platforms. And as I mentioned earlier, with NFS over RDMA, we can start to deliver performance levels that are consistent with what people would otherwise only see with SAN protocols or potentially direct attached storage. And so everything gets different in the VAST era, as you don't have to make the same considerations around how to store interior data as you did in the past. You don't have to make the same protocol-oriented decisions that you did in the past. And all of that is well and good. Being able to consolidate all of your data onto one platform that's entirely of flash is, of course, a nirvana for a lot of customers. And we make it possible not only by building this infrastructure that is both fast, scalable, and easy to deploy, but also by fundamentally innovating in three different areas. The first, as I referenced earlier, is our QLC flash translation. And with this, we get to a point where we extract about 20 times more endurance from low endurance flash than what the drive manufacturers themselves will advertise. And this becomes a big reconciliation against the traditional storage companies that have to sell very expensive flash. The second order of savings is basically by fielding that infrastructure for 10 years, which is something that we provide a guarantee for, that you'll never be able to wear out your QLC flash within 10 years. And we write fixed flat maintenance contracts that go out over 10 years. The third order of economic optimization is around data protection. And we have these new class of erasure codes that we call locally decodable codes that break a fundamental trade-off that's always existed between the overhead that you pay for resilience and the resilience levels that you should expect to get from your cluster. In our case, we bring the overhead down to just 3% while giving customers a 60 million year mean time to data loss. So that allows us to save up to another 66%. We're talking about Splunk today. Splunk is an architecture that popularizes triplicated direct attached storage. And in our case, we save customers dramatically against that type of model. And then finally, in terms of providing more free space from that infrastructure that has low overhead, we've pioneered a new type of global data reduction that we call similarity-based data reduction. And this capability has all of the benefits of deduplication in that it goes global across all of your namespace, all of your storage cluster. But on the flip side, it's not a coarse pattern matching like you have with deduplication. Our pattern matching goes all the way down to single byte levels of granularity. And so what we're able to do is to find patterns in places where customers never really thought that there would be an ability to optimize on a global basis. And this similarity-based data reduction allows us to really compress data down in environments. And for example, in Splunk environments that may be triplicated, even though you still store your data in triplicated buckets, we can reduce data down beyond just 3 to 1, but even 3.5 to 4 to 1 data reduction. And all of these savings compound, very low cost flash, 10 years of longevity, 3% overhead, and global data reduction. And so with that, now we'll kind of turn our attention to our application play that we're currently working on with respect to customers that are deploying large Splunk infrastructure. And we'll get to the kind of the takeaway that you all sign up for this webinar for. So with respect to our value proposition with Splunk, it's very simple. We think of our architecture as basically providing a performance level that exceeds what Splunk recommends for hot data, but at the same time pioneering all new storage economics so that you can think about the cost of infrastructure more akin to what you would spend for your cold storage buckets. And once you can move to network attached storage that is scalable to exabytes, that brings all of the state off of an index or node, We believe that functionality gets much easier to size for, and the system is easier to upgrade, and it's easier to scale than has been done in the past. And so if any of you have ever configured a Splunk system, you're probably quite familiar with the Splunk storage sizing guide that is available online. This is a great utility that helps people understand what they need. But the challenge with architecting Splunk tiers is that it essentially requires organizations to have an ability to predict the unknown. And the reason for that is that, that customer behaviors and your vendor behaviors aren't always static, and you have user search behaviors that change over time, and people are looking for different patterns within different ranges of data. Splunk will occasionally introduce new modules that do have an impact on storage, and you need to size for those appropriately. You may have shifts in your compression ratios, you have different retention period changes. Customers can receive more ingest on a daily basis, and then you have other considerations that are starting to be popularized around virtualizing or containerizing Splunk. And all of this requires, when you architect your Splunk clusters, if you're buying on a periodic basis, to really have a good understanding of not just what's happening today, but what will happen in the future. And that can be a really tricky situation. Now, Splunk, they have two different models of long-term storage that customers can choose from today. Today you have the kind of the classic mode of Splunk where you have hot data that's organized either in direct attached storage or SAN attached storage. Then you have cold data that can be distributed across direct attached, SAN attached, or network attached storage. Cold buckets are supportable with NFS. And considering the current model, you choose a replication factor. If you're using direct attached, often that's triplicated. And the same holds true for both hot, warm, and cold buckets. Cold bucket performance is typically pretty low, so users don't have a real very solid expectation of cold performance in these cases. And we understand from other vendors that PSIDX compression can implement a significant amount of overhead for long range or rare searches in terms of performance. And then finally, as customers go to upgrade, we've encountered customers that have pretty light replication factors, even some that are single instances of data within their indexers. And as you have a lower replication factor, customers have to move data around their cluster as they go to upgrade it. And that can be very bad from a time to upgrade perspective. Now, the second option that you have is a capability that Splunk brought to market just last year. It's a capability called SMARTSTORE. This dovetails off of some of the work that they're doing with Splunk Cloud. The difference here is that as opposed to classic cold buckets that can be on direct attached, SAN attached, or NFS attached storage, you can consider an alternative of using S3 storage as the means to store your long-term data. A lot of the S3 vendors like this because you don't have the same amount of replication that you classically have with cold, hot, or warm, and most of the object stores in the marketplace today, they don't have data reduction, so that becomes a pretty costly endeavor if you were to use classic NAS systems or object storage for cold buckets. But as you can use them for SMARTSTORE, that's single instance. So it's more efficient from a storage model perspective, excepting for the fact that Splunk advises that you keep 90 days of SMARTSTORE cache and warm. So if you have clusters that are being built for less than 90 days retention in total, doesn't always make sense. And you have to be sure to size for that cache, which is typically advised to be kept in a warm or a hot bucket. And of course, that has a cost implication, particularly if that data is going to be replicated. And then you also have the same compression overhead. The performance from a cold bucket perspective, let's call it in the case of SMARTSTORE, can be even lower than a classic NAS-based or SAN or DAS-based cold bucket. And the reason for that is that you oftentimes are dealing with a slower protocol that is more cloud-oriented. Oftentimes those S3 stores may not even be in your same data center. So all of these things need to be considered when you start to architect beyond the classic model. But from an upgradability perspective, getting that data off of the indexer, of course, helps in the time to go and upgrade your Splunk clusters. Now, There are some other considerations that customers have to face when they're looking at SmartStore. First is that you can only set a search factor of 1. You have to retain more than 90 days to make that make sense, because otherwise Splunk advises that you have to cache 90 days within your indexers. Splunk doesn't advise that you use SmartStore for things like rare searches or long look-back searches, and they don't offer the same data integrity controls. You also can't roll buckets off into Hadoop from SmartStore. So, so these are considerations that people need to think about as they're starting to architect the next version or next generation of their Splunk clusters. And so if I kind of go back to the classic model, you have hot and warm that are supported with either direct attached or SAN attached storage. And today that's about, Splunk advises that you need as much as 1,500 IOPS per indexer. Whereas with the cold tier, the requirements are less because the expectations are less. And so in this case, the Splunk advises that you need something in the order of around 350 IOPS per indexer for cold buckets. And VAST has been doing some testing, and the interesting thing is that when you can move to a next generation NFS-based architecture that provides sub-millisecond latencies and is built entirely from Flash, well then the same sort of historic performance experiences that customers may have encountered with NFS don't necessarily apply. And so we've been doing some work with the Splunk test tool. It's called the Splunk parser for Bonnie++. And what we've been able to see is that from a single indexer, a cold bucket can be searched, well, a cold bucket configuration can exhibit as many as about 6,000 IOPS, which is in and around the range of around 400% more than the single mount performance requirements that Splunk indicates that you need for hot buckets and very heavy workloads. Now that's for a single mount point in the NFS context. That's the machine mounting via a TCP connection, a single server on the VAST cluster. What we've also seen though is that if you start to aggregate mount points within a cluster, you can see even greater performance. And if we measure performance just by a standard industry benchmark tool called VDBench, we've seen as many as 70,000 random read IOPS per single host. So now you can start to consolidate from a performance perspective more VMs or more containers within a single node as Splunk can support that. So the other consideration is that as search clusters get larger, we have the ability to, of course, scale out our infrastructure as well. And what we have the ability to do is build a distributed all-flash NFS infrastructure that can scale to millions of IOPS. So as far as we're concerned, there's no practical limitation to how large you can build these clusters, and we're starting to work with customers on some very, very big implementations. And the solution looks as such. So we, as I mentioned earlier, we have support for S3. We also have support for NFS and SMB and container interfaces. And as we looked at the problem, we came up with a reference architecture for the few of the customers that we're working with that essentially tries to first marry in with what Splunk would consider a known good implementation. And so hot data is maintained on a local direct attached disk through some replication factor. And then the objective is to make that as thin an amount of infrastructure as possible so that customers can more quickly start to benefit from the capabilities of VAST. And as a result, we advise that customers then roll those buckets onto into a cold bucket that's backed by VAST, which is built entirely of Flash. And so one day of data in hot, and then everything else basically in a cold Flash bucket. And as your data gets in there, then you can start to scale capacity as much as you like, and there's no direct correlation to what your ingest cluster is sized at. You get essentially better than hot search performance. And there are no limitations on the types of searches that you can do. So you can do rare searches, you can set your search factor to whatever you'd like to. And with data reduction, you can set a replication factor to whatever you'd like to. And there's really no penalty at the storage level because of that. You can roll data off to Hadoop clusters and pretty much it enables you to do whatever you want to do on any time series of data without restriction. And of course, the reason that you can do that is because we've pioneered a new cluster architecture that introduces cold storage economics. And I've talked about the savings that we exhibit. This comes from combining a new type of flash that can be deployed over 10 years with a new type of erasure code, and then data reduction that, as we apply it to Splunk environments that have compressed data both for indexes and raw data, we can still see greater than a reduction factor that's greater than the replication factor in a cluster. So as we think about this from a capability perspective, we start to compare the different types of configuration choices, and we use some of the reference architectures that have come from the large vendors in this space, and we start to compare the different capabilities. The first thing is, because of the data reduction capabilities, because of the very thin erasure codes that we have. Sorry. It's very strange. We're in a conference room that has a random phone in it. Okay, so because of the thin erasure codes, because of the data reduction capability, what comes out of it is that you just need a lot less physical capacity to support a specific cluster requirement. And the interesting thing is you start to depopulate the indexer nodes from having to own and manage data. The next thing that happens is you can start sizing Splunk clusters essentially for the performance that you need, and you no longer have to add another dimension to sizing, which is the capacity that you want to store. And so as we compare this approach versus all flash-based S3 storage capabilities using SMARTSTORE or VAST's COLD.FLASH approach, what you can see is that there's just a dramatically smaller amount of flash that's required to hit the same exact objective. And you can start to scale capacity completely independent of indexer performance. So we believe this changes the search paradigm, because you can now size very effectively, and as you need to grow in one dimension or the other, either in terms of search performance or capacity, both of those are now disaggregated and scale as you need them to. We have started to work with a number of customers on this. We're working with a large web scale company that uses an extremely large Splunk real estate. They have clusters of over 1,000 indexers. And they've come from a place where, and in this case, this customer comes from a place where they had a very low replication factor, a replication factor of 1, and just local node data protection to survive against a hard drive or an SSD failure. And they kept the rest of the data in cold bucket. It was only 30 days of retention, so the 90-day SMARTSTORE caching model didn't entirely work for them. But more importantly, as they considered the VAST architecture, they essentially kind of moved beyond this paradigm that cold searches needed to be slow. And by moving all but just the minimal amount of data off of the indexer node, then they could start to upgrade much faster than they could previously. And of course, there's a resultant data center power and cooling savings that comes along with reducing down infrastructure and no longer triplicating media in order to support that. So there's a whole raft of advantages here that range from CAPEX savings to lower operational headaches to always fast searches and lower impact on the data center. And we're now working on these types of projects with a lot of customers in the space. Not all of them are ingesting a petabyte per day, but the benefits kind of apply regardless of the scale that you're operating at, assuming you're over, let's say, 500 gigabytes of ingest per day. And so that's really the story. That's what we're here to talk about today. Our COLD.FLASH architecture, and the value for Splunk is that you get always fast searches. The architecture is future-proofed. So as you start to evolve your Splunk strategy, as users or researchers start to interact with search clusters differently, you don't really have to worry about where their data is oriented. It's fully disaggregated, so you can scale indexers for performance, scale your storage for capacity, And it keeps within the hot-cold schema so that you don't have a series of compromises you need to consider in terms of how you search. The savings can be pretty radical, particularly as you start to measure against direct attached or SAN attached clusters that use very expensive flash technology. Ours changes that equation entirely. It's completely standard with respect to how Splunk advises customers build their hot and cold buckets. And it's simple in that you don't have to go through the complications of moving data around your clusters as you're dealing with low replication factors, if that's something that you want to do. And the one thing that we're starting to play with, we don't know exactly if all the customers can benefit from this, is we have had some customers start to think about, what if I increase our replication factors beyond what I typically did with vast similarity-based data reduction? You don't have to pay more as you increase your replication factor because everything is globally reduced. And so how that changes, at a minimum, the ability to survive a search in the face of server failures, that's an easy one. But there may be other benefits there that we haven't really considered. So at least in cases where customers have a replication factor of 1 previously, they can move to a replication factor of 2, which allows them to increase their search factors in cases where they absolutely need to guarantee that a search gets completed within a certain period of time. But there may be other benefits that we haven't considered. So we'd love to hear if you have any questions about this, and we'd love to hear your thoughts on our architecture, and love to talk with you a little bit more about how you think about future sizing. It's also important to consider that this isn't the only use case that we support. We launched a company in the beginning of 2019 with this idea of universal storage, one platform that you can deploy for all of your data. And this the solution architecture that we're talking about today is entirely consistent with that. So this is one platform that you can use for everything from AI to backups to containers to HPC. And increasingly, we're seeing customers move beyond the direct attached storage model as protocols get better, and the benefits of shared storage on the network, and as networks get better, as the benefits of that gets better understood. So this is an example of that capability today with our COLD.FLASH architecture. We feel that it gives you better than direct attached storage performance at cold economics, network attached storage prices. So pretty simple one today. Thanks everybody for your time. We'll open it up to questions, and we do have one, I think. Oh. This is a very long question. Okay, so I'm just reading through it 1 second. The first question is, you said most S3 vendors do not support data reduction compression. It seems that Minio, for example, does. Is that really true? As we think about most of the object storage offerings in the marketplace, it is true that most of them don't support deduplication. They don't support global compression. So I would say absolutely that is the case. I'm trying to look for another question in this. Customers saying they're seeing queries using SMARTSTORE objects that are exceptionally slow. Of course, this solves that, and we're happy to help customers benchmark against that. Yeah, I guess that's the extent of the question here. Some more commentary for us internally. So, okay. Yeah, that's one. Any other questions that people might have today? No? Okay, well, we will. Oh, question from Ken. What are the block sizes used? We have a variable length block size that's not how you would typically encounter storage configuration in the classic sense. So we are completely variable in length, which means that you can store data in whatever segment size that you'd like. We don't burn any capacity when customers store underneath a certain block size. Everything gets aggregated in Flash. Okay, I think that's it for questions. So Great. Thanks everybody for your time, and we look forward to talking soon. We've got some big announcements that are slated for early April, so stay tuned for those, and we'll publish this back to you in the next couple days or so in case you want to rewatch it or send it to your friends. Thanks everybody again, and enjoy your day. Cheers.